Alright guys, if we look at the big quiz, FRQ part, one thing that a lot of people struggle with is drawing pictures, specifically free body diagrams. On the FRQs you had two of them. One of them was this tightrope one, and you had to draw some pictures of this gal on a rope here. Now for the others, there were a bank, and there were 4 possible problems, and most of them had you draw pictures of a free body. So let's just talk briefly about this. Here's a tabletop. This is a book. This is what I would do if we were in class. I put the book on the table and I'd tell the class how many forces are acting on the book. Alright, let's draw an FBD of the book. Right? And so what we would draw is we would draw a dot. Say, what are the 2 forces? Oh, well, I guess there's 2, because I said, what are the 2 forces, right? Well, if it's on Earth, and about all of our problems are, then we have one force going straight down towards the center of the Earth, which I like to call FG. And what we're going to get y'all in the habit of doing is not just saying FG, but you need to define what it is. So what is it? In this case, it's the force of the Earth on the book. This is called a field force. The book and Earth are not actually touching. I have it drawn on a tabletop. And if we were in class, I would put the book on my table up at the front of the room. And Earth and the book are not touching. If the book is sitting on this table, Earth is down here. Right? It's the same thing if you take your pen and you pick your pen up to a certain height and you let it go. The pen and Earth are not touching. So what's going on here? Right? This is called a field force. When 2 things are not touching. So this represents the field force of Earth pulling on the book. Now there's another force. There has to be. If this were the only force, then the book would accelerate down through the table and hurtle down towards the center of the Earth, and it's not doing that. So there's another force that goes up, equal in magnitude, opposite in direction. And this is the force of the table. So a lot of people would write that force table, something like this. And we would have to define what that is. What is this force table? This would be the force of the table on the book. Those 2 things are directly touching. This is called a contact force. Okay? And so we can have contact forces, we can have field forces. And that's it. Those are the only 2 types of forces that you can have. So some of you, when you're doing things, when you're doing problems, when you're doing your quiz, I think some of you try to create forces that aren't really there. Here's an example of one that I had on the quiz, right? There's a table, there's a ramp, the ball rolls down this ramp, and then it comes horizontally off of the table. So it actually comes off in the X, and it moves in this curved path. Okay? This would be the same thing as if I throw a ball horizontally, like if I'm pitching. And the ball will come out of my hand in the X direction. And so, first part here, it said to draw a free body. When the force is acting on the ball, the moment the ball is no longer in contact with the ramp or the table. And so the ball has come off of the tabletop. And this could be a little confusing because this has somewhat of an angle, and I wrote on here the ball comes off horizontally. This is very similar to our cliff problems, where we had a cliff. In fact, it is a cliff problem, where you have your cliff, and the thing is going to come horizontally off the cliff and go do-do-do-do-do, right? So it has some velocity. And I just wanted people to draw, as soon as it leaves the cliff, and it's no longer physically touching the cliff, what were the forces? And I got all kinds of neat things. Okay? When it leaves the cliff, okay, and it's moving horizontally, and there's no air, there's nothing touching it. There's no air touching it, it's no longer on the cliff, it's not touching the ground. There are no contact forces. So all I was looking for is for someone to draw a dot. Okay. And there's just one force. If I throw a ball and there's no air, when the ball leaves my hand, it will start to curve downwards because the force due to gravity is going to pull on it, and that force acts one way and one way only. It always acts down. This is the picture I wanted right here for this problem. The free body of this thing coming off of that ramp. It's just one force going down. It's a little weird to have this one force. That normally wouldn't happen because we would have air acting on it, but in this case we don't. But see, because its path is curved and because it starts horizontally, I had a lot of people drawing something like this and saying, well, this is the velocity. Or instead of calling it the velocity, they called it force then the x. I had all kinds of things. No. Just one arrow straight down, all that I wanted. That is a field force. That is the force of Earth acting on that object. I've already had you guys look at notes and watch videos on this, but I want to talk about this upward force right here. The force of the table pushing up on the book. This has a name. It's really not force table. It's called normal force, force normal. And the word normal means perpendicular to. So if I draw a dotted line to represent the two surfaces that are in contact, right? Normal means perpendicular to. It's a right angle. So a normal force is a contact force that occurs when two things are touching, and it acts perpendicularly to their surfaces. So here I have a normal force. So I wouldn't call this force table. I'd call it force normal. Okay. Now, I'm going to add a little more complexity here. What happens if I pull the book to the right? I'll call that force pull. Okay. This is a little tricky. Let's say that I move it with constant speed. So I say, and this is what I would do in classes, I would say, all right, V is constant. Lord, I don't need to write that. V is constant. V is constant, then our acceleration is 0 meters per second squared. And so I ask people, okay, let's draw a free body. Right? How many forces are acting on the book? Well, to answer this, one of the answers is it depends whether you have friction on or off. Okay, so let's do one with friction off first. So friction is off. I draw my dot. I know I have my force pull going to the right. So that's the force of me on the book, force pull. Now if the book's not going up or down, if it's not going up or down, then I have some balanced forces in the y-axis. My downward force I could call Fg. My upward force is that force of the table pushing up perpendicularly. That's called normal force. So there are all my forces defined. One thing I didn't do is I didn't put x and y on these forces. My force pull is in the x, my Fn and my Fg are in the y. Now if we have just these three forces and we don't have friction, then this will accelerate to the right, and our acceleration will actually not be 0 in this case. So I need to mention that that's not something that can actually happen with only three forces. Now if we add friction, then we can have this where it will be, this will be the case. And if you've been watching videos and looking at the notes, you'll know that friction is a force that acts, seems to act against us, that seems to take things from us. I tell students that friction is a force that opposes the intended motion. And so if we intend the book to go to the right, our force of friction would be to the left. And I like to call it F of Fr, force friction. I tend to draw it in red because it's opposing our intended motion. What is it? Force of friction is the force of the table acting on the book, and it acts parallel. So if the book is moving to the right, friction is acting to the left. Now if we have constant speed, if our velocity is constant, then all these four forces should be balanced. All of the arrows should be roughly the same length, and I've tried to do that as best I can. And so your force pull will be equal to your force friction, and this book will actually move across the tabletop at a constant speed. Alright, what happens if we do this? What happens instead of pulling the book in the x-axis parallel to the ground, we pull the book at some angle? What will our FBD look like? How many forces do I have acting on this thing? I've got my force pull, so I can draw that in there. F pull. Of course, I need to define what all these forces are. Now, if it's still sitting on the table, I guess the question here is, if I pull the book at this angle, will it come off of the tabletop? It's like you're pulling a box along the ground with a rope. So I want to pull this book across the tabletop. I'm going to pull at an angle. Why would I do this? And that's because I'm human and I stand upright. And so the book will slide along the tabletop. So if it's still in contact with the table, then I have these two forces. I have a down force, it's Fg. I have an up force, which is Fn. So I still have these two forces. And if I include friction, which way does friction go? Well, if the book is moving across the tabletop in the x-axis, then friction will still oppose me in the x-axis that way. This confuses folks, and they say, wait a minute, what's the book really doing here? Well, it's moving across the table. It's not actually going that way, it's moving this way. It's like mowing. Your mower, if you've ever seen someone mow, here's the ground, here's the lawnmower. The handle goes like that, right? So the force is exerted along this handle. But which way does the mower go? The mower goes that way. The mower doesn't go through, the mower's not going this way. The mower's going that way, right? So, same thing here. I'm going to pull the book at some angle, but the book is going to move along the tabletop, and I want it V to be constant. So I want the velocity of the book to be constant. These are all my forces. Those are my real forces. Now, if I asked you to solve a problem, for instance, find F pull, there's some angle here. There's some little angle theta. So what I would have to do is, hopefully you can see that there would be a little right triangle right here that I could create, and I could do some trig. And really, I screwed that up. I like to color code things. So my x part of the triangle would look like that. You can call that F pull in the x. And then my y part, F pull in the y. And so, knowing what theta is, I could figure out what those components are. Now, if we go to that problem on the quiz, so here's our problem on the quiz, and it asked you to draw an FBD of what's going on here. Right? And so, rope is massless. The person is going to have gravitational force going down. That's the force of the earth on the girl. So that would be down this way, Fg. And then you have two forces going, oh goodness, you have two forces going along the ropes. One going this way, and one going that way like that. And so my FBD would be something that looks like this. We call this T. The thing about this is all one rope. We can break it up into two pieces, but the rope, since it's massless, the tension in a rope at all places is T. And so then I could add, x's and y's. This could be my x right here, and a y. I have an x here, and a y there. I can make little right triangles, just like I did here. Made a little right triangle, and then I can solve things.